this is Friday's lesson. So you should have watched the end of 2.4 on Wednesday. Thursday was your work day, and for most of the classes, somebody would have been in here to answer some questions. One of our calculus students or pre-cal. So today, this should be a review. Fundamental theorem of algebra. So just as a refresher, we're going to write out what the fundamental theorem of algebra states anytime you're trying to solve a polynomial. So the fundamental theorem of algebra. So it says an nth degree polynomial has what?
As n solutions.
N complex solutions. And so when we say the word complex, it means what type of numbers? What are the two main types of complex numbers?
Real or imaginary?
Real or imaginary. So it could be real or imaginary. All right. So as we remember that, and this is going to be really a refresher of what we did earlier in 2.3, solving polynomial equations. So if we get started, just with a typical, it could be something like x squared minus 9 equals to 0. We'll see that there should be, because it's a second degree, we should have how many solutions? Two. And you can either factor, or I like to just isolate here. So x squared is 9, x is plus or minus the square root of 9, which is plus or minus 3. And there's your two solutions, okay? So what we want to look at now is, since we've just got through looking at the imaginary numbers in the last section, now we're going to see a lot of our solutions that we have to write the imaginary numbers. So there's a little bit of a rule for imaginary solutions. So we're going to write this rule out. So point number 2, imaginary solutions occur in conjugate pairs. So this is always true when you're solving a polynomial. So if we're solving, when solving a polynomial equation, if x equals to a plus bi is a solution, and when we're talking about this form, b cannot equal to 0 because we have to have the imaginary number, then blank is also a solution. So what do you think that means?
A minus b.
A minus bi. So just like we looked at the other day with our conjugates when we're dividing, now we're guaranteed that that's going to be a solution. So why do you think that this is going to happen? So what might be the reason that that's going to happen?
Because the imaginary part is under the square root.
That's exactly right. So when you have when you have an I, it comes from having a negative under the square root, and what's usually out in front of square roots when we're solving?
Plus or minus.
The plus or minus. So a couple of easy ones to look at. So for an example, so if x equals 3 minus 2i is a solution, then we know what else would be a solution?
3 plus
3 plus 2i. If x equals 5i is a solution, then we know what would be a solution? Negative 5i. So maybe just to show the second one, because that's a little bit easier, we call this example 2. If you solve x squared plus 25 equal to 0, just like what Natalie said, is that when we go to solve this, I'm using the same method over there, move the 25 over, but now it's negative. And anytime you solve an equation with a square, when we do square root, we must put what in front?
Plus or minus.
Plus or minus to get all our solutions. And so right here, when we do this, that's where we pick up our pair imaginary solutions. So what is the square root of negative 25?
Plus or minus 5.
Plus or minus 5. Okay. All right, so basically there's gonna be nothing new for this lesson. You're gonna go through and solve our polynomials. Now I picked two easy ones, but we're gonna ramp it up a little bit. And you may get an imaginary solution. Just note that you can't just have one imaginary solution. You could have two, or you could have four, but they're always in pairs. Okay, so what I thought I'll do is I'm just gonna give you some examples. We'll work through them together. I'll let you start and work it, and then we'll go through and see if any have a imaginary. So let's get started with this one. This is number 28 from the book. X to the fourth plus 29x squared plus 100 equals to 0. So we're back to, now we've got our fourth degree polynomial. So according to the fundamental theorem of algebra, how many solutions should there be?
4.
4. Now we have two ways to solve, as we've learned before. We can either try and factor, if I can't isolate like I did here. We can either try to factor, or we can use rational root tests. Do you have an idea in mind on this one?
Factoring would be nice.
Factoring would be nice. So what tells you that we probably can factor this one?
The x to the fourth and x squared.
Yeah, so since it goes 4 and 2, that is a cue that this is of the what type? It's the quadratic type. It's not a quadratic, but it's called a quadratic type, which means it can be factored. So we would start the first of the parentheses with what?
Oh, x squared.
X squared. And then what question do we have to ask ourselves?
What two numbers multiply to get 100 and add to get 29?
All right, so can you think of two?
25 and 4.
25 and 4. And so now we have we've got it factored. It's good enough. Now, so let me ask you, is this considered completely factored?
Yes.
If for real numbers, yes. However, to be completely factored, it would have to have 4 factors. So technically, no, because since it's a fourth degree, it should be like x minus x plus. And I know it looks weird, but we know the solutions to this. So technically, x minus 5i and x plus 5i are considered factors, even though they've got the imaginary. Now, we wouldn't try and factor it. We're just going to solve these. But it's not completely factored until you have all the 4. So as a fourth degree, it has to have 4 pieces. But we're not going to factor these. We're going to set these equal to 0 and solve. And we already know this one. We just did this, so that's plus or minus 5i. And we're going to solve this one very similarly, right? So we just move the negative 4 over, and we get plus or minus the square root of negative 4, which is plus or minus 2. So, how many total solutions?
4.
4. Are they imaginary, and if so, did they occur in pairs?
Yes.
Yes and yes. Okay. All right. So let me ramp it up a little bit. Let's give you one here that maybe it's not so easy, and you have to think a little bit. Let's try this one. Okay, so this one I'm going to stop. I'm going to just let you work it, see if you can figure it out. If you want to kind of see what she does,
Oh no.
put pressure on her a little bit. You really only have one choice on the method. So hopefully you can,
Okay.
we can see what she does. So yeah, you're gonna commentate a little bit, right? So she's going rational root test on this one. And also I'm gonna give you a little hint. Everything is positive. So since everything is positive, would it make sense that a positive can be plugged in to give you 0? Would that make sense?
No.
No. All right, so a little technical issues, but we're good. We went in and put the quadratic formula. If we sub in b squared is 64 minus 4, a is 1, c is 17, all over 2. So let's see. 4 times 17, what do we get?
68.
68. So we have negative 8 plus or minus 64 minus 68 gives us a negative 4 all over 2. And what is square root of negative 4?
2i.
2i. So we've got negative 8 plus or minus 2i over 2. And what did I show you yesterday about putting it in standard form?
Split the fractions.
Yeah. So if we do negative 8 over 2 plus or minus 2i over 2, we get negative 4 plus or minus I, along with our x equals negative 2, and there are our 3 solutions. And here, our imaginary solution occurred in what?
Conjugate pair.
Conjugate pair. So that's it. I'm going to give you the assignment here. I want you to work on 5 through 37 odd in section 2.5, and that's using these methods that we talked about today. And then I'll see you hopefully on Monday the 13th. Thanks.